Hello, everyone. My name is Fady Abouelghit. I will be your instructor for session number 3, covering complexity and algorithm complexity. Now, I hope you paid some degree of attention to the previous session, because this one builds on the previous very slightly, not drastically, but very slightly. We'll be discussing a very topic that I consider to be very interesting mentally, and I hope you enjoyed this as much as I do. Okay, without further ado, let's jump to the problem. Okay, we'll be discussing four primary areas. Primarily, popular optimization problems, complexity analysis, complexity classes, and we'll formalize with a traveling salesman problem, which is one type of problem that you can expect to find. Right. So, problems. We've got one of the primary problems in a big industry, which is the airline industry. We've got flight scheduling. So, what is flight scheduling? So, I'll use our national flag carrier, the Egyptian flag carrier, as an example. Egypt Air operates in a plethora of cities and airports. You have to have flights to Dubai, London, Brussels, Holland, Saudi Arabia, and a lot of different countries. And each of these flights have a resource allocated to it, or a number of resources, including, well, the pilot, of course, flight crew, and one plane, okay, at any given point in time. So you need to find the optimal way to schedule and assign planes and crews to flights. What the constraint here is essential, because what we're trying to do is get the best allocation while minimizing delay, cost, and total distance travel, because the airline industry is a very expensive business, and you wouldn't want to spend a lot of unnecessary money on this. So that's one problem. The other problem is back on the ground with delivery routing, to set placeholders into perspective in e-commerce platforms in Egypt, of which we have a lot. We've got Rabbit, Breakfast, Talabat, Noon, Amazon. All of these companies face the same problem of delivery routing. So similar to planes, you've got cars or vans or bikes, depending on the type of business, that have to pick up a certain number of orders from a certain number of warehouses that are not all in the same place, with the conditions that hopefully all orders must be fulfilled. So you have to get to each and every one of your customers, as well as minimize cost and distance. Okay, let's try to put this in a graphical setting. So on the left here, we have the flight scheduling problem. We've got Cairo, Istanbul, I believe this is London Heathrow, Charles de Gaulle in Paris, and Dubai. So which one should you go to first? And you have to visit all of them. Should I go to Istanbul first, or should I go to Dubai, then go to London Heathrow, then Charles de Gaulle, then back to Cairo? It's very limited, but a very fundamental issue, and the answer would be let's try, maybe. Let's try and see all the different combinations, starting with Cairo and ending with Cairo. And we'll see which one gives us the most optimal route in terms of costing and flight duration, etc. The another problem here is the delivery routing problem. So we have two warehouses and two vehicles in yellow and in purple, and a couple of orders that are in your roster. So C1s through 6. Uh, Ask yourself this question. Sure, the graph shows you that the purple van goes to 6, 4, and 3, but why should it? Why shouldn't the yellow, after visiting 2, visit 3 and then come back to the warehouse? Or why shouldn't, analogously, 4 visit C2, sorry, the purple van visit C2 and then back to its warehouse? Nothing in set stone, and normally any normal person would say I'll have to try and see, but there are algorithms and there are ways you can approach this. And we have a couple of things that we can say that we have in common between this subset of problems, and you can ask yourself a series of questions. Um, can you guarantee that the solution exists? And given that there is a solution, if you find one, is it the best one that you can find? And given these two questions, you can ask yourself a third question. How long will it take you to find that solution? And given these three questions, you can ask yourself a fourth question, is what happens when the number of nodes increases or the number of places you need to visit increases? So taking us back one slide here, what if there are no longer 6 orders on the right? What if there are 10 or 20? How would you approach the problem then? Of course, the answer would be I'll have to try and check or at least apply the algorithm and to see whether or not we'll be able to reach a solution or not. This is all purely subjective. Now, what we're trying to do is move it from a subjective perspective into an objective perspective. So we need to have a formal way of measuring difficulty without just saying, oh, this is difficult or this is easy or this is tough. And this is bringing us to a concept called complexity analysis. Uh, Now, for those of you who are exposed to complexity analysis before, I hope you find something out of this. And for those of you who aren't acquainted with complexity analysis, I hope you find it interesting and informative. So what we're trying to basically do is primarily we're trying to compare. Okay, so what we're trying to do is compare one type of difficulty to another type of difficulty. No two difficult problems are the same. They could be difficult in different ways. So to compare, you need to determine the type of difficulty, and this eventually guides your optimization problem to help you test for solution feasibility, for example. This brings us to what is commonly referred to by Big O notation. Big O notation is a very common notation where you explain how the problem scales on two facets, time and also memory, computer memory, of course. So, for example, assume you have an infinite number of nodes to test. We do not have infinite memory. And assuming you have a lot of nodes to look through, but you don't have enough time to look through them. So you need infinite time to look through them, in which case you also don't have an infinite. Unfortunately, we don't have an infinite period of time to look for a solution. So this brings us to O notation. And what this basically explains is, for example, starting with O of 1, you have a basic uh, indexable solution. So if you're looking for something, you want to look for your keys, want to look for your pen, you can say, oh, here is my pen. This is O of 1. I know where it is and I know where to get it from, and you just find it. So O of 1 is constant in that sense. You start to increase your complexity by going up from logarithmic complexities to linear, and then all the way up to exponential, which is considered the worst case complexity in this case. So on your axis, you have input size in front of runtime on the y-axis. And for example, with linear, which is here, you have linearly scaling complexity as n increases. So n here would be, for example, the number of nodes you have in the problem. Okay. And the worst case being n factorial, which of course means that you're very sensitive to the size of the nodes you have in your problem. So a very small increase will give you a very big leap in complexity, and this is of course uh, very far from the ideal case scenario. Let's break it down. We have three primary, let's say three primary problems. And let's try to put some problems let's try to cluster them and give them context so that you try to fit things where they could be in terms of complexity. Let's try and have this exercise. O of 1. I give you an example on it. How about of log n? Let's go back a slide. O of log n. Take a moment to think about it. O of log n. Maybe if you're familiar, you might say something like binary search, which is a way that you use to search for things in a list. How about O of n? O of n is easy. O of n is looking for stuff, for example, in your filing cabinet. So if you have a certain number of files in your folder, for example, and you want to look for a specific file, will it take you out of 100 files, 5 files to get there? Maybe it's the very last file, so you need to get to 100 files to get to the file you want. This is where n comes in. And then moving to exponential, I'll stop at n squared, for example. We've got nested loops. So if you have a for loop within a for loop, you keep on looping in a nested fashion, this is O of n squared. These problems all fit into different buckets. So you've got three main buckets, P, NP, and NP hard. P is practically easy to solve. Okay, it's a decision. You can find the answer straight away. But moving to NP from P, it's a bit of a transition because this time it becomes not so easy to solve, but maybe given that you solve it, it's easy to validate and verify. An example for this would be Sudoku, which is a game that I'm not very good at, unfortunately. And NP hard, you have which are termed to normally as master key problems. It's at least as hard as an NP problem. And a type of problem that is NP hard is the traveling salesman problem, which we will explain very shortly. But before I do, let's explain a fourth type, which is kind of a subset of the NP class of problems. It's practically NP. It's called the NP complete. It is, in fact, NP, and it's practically a solution, of course, that has to be verifiable. So if it does have a solution, can practically verify the solution in polynomial time. That's one condition for it to be NP complete. The other condition is that it is NP hard. So as we can see, it's kind of an overlap between NP and NP hard. And a fun teaser for you is P equals to NP. Um, and think about it this way, if you can reduce um, an NP hard problem or solve it efficiently, sorry, an NP complete, not an NP hard, if you can approach an NP complete problem, um, what do you think that would make of the NP in a generic sense? So if NP complete is solvable efficiently, wouldn't all NP problems be solvable? And of course, this is a million dollar question. Just a fun problem for you to look into. Maybe one of you will be able to solve it in the future. Moving on to a graphical representation of what we like to call as the, or what everyone likes to call as the traveling salesman problem. Okay. The traveling salesman problem dictates that for every n nodes or cities, you are due to find the absolute and utmost shortest route given two certain rules for you to satisfy a solution. The first is you have to have a common start and ending point. So assume you always start at the zero node, you have to end at the zero node. That's one. The other one is you have to always visit every node once. So all the nodes have to be visited, but you cannot visit any given node more than once. This is, of course, NP hard, and it has a complexity of O to the n or n factorial. It's O of n factorial. What does this mean? Well, it means if you have 20 cities, you'd have to search for this many number of solutions or unique routes, which is, of course, an insanely large number to look into. And you can ask yourself the question of whether or not it's actually solvable or not. In this case, the answer would not be straightforward. However, what if we choose to change the formulation a little bit and add a condition on top of it? And we ask ourselves, is there a solution where a given route is shorter than 500 kilometers? This is a decision that would be NP complete as opposed to the previous formalization, which was NP hard. Okay. Now for a brief illustration for you to put things into perspective. We'll try to quantify the runtime constraints for three problems. We pick three easy problems for us to model, and we can try to solve them using a very basic code that you can write that practically applies one of the algorithms to three different types of problems. Okay, problem one, which is a P problem. So assume you have a list, for instance, a list that is starting at 1 and ending at n. And I'll assume that n here is equal to 5. Let's say 5. This is a very bad 5. Assume that n equals to 5. So this is a slowly increasing list that goes from 1 to 3 and all the way to 5. And the problem would be I want to find the max value of this list. So assuming I don't know that n is equal to 5, I will start on my first iteration and hit 1. So I'll assign the largest number in my universe to 1. Okay, what happens when I move on to the next iteration? Well, that's easy. I'll go on to the next number and then I'll see, well, is 2 bigger than 1? And of course, the answer would be yes. Then I would assign the largest number to 2. And I will keep going until I hit the end of my list and I assign 5 to be my largest number. This is an O of n problem. Let me mark this in red. If I can change the color. I don't think I can. Yes, I can. Okay. Submit. This is O of n in terms of complexity. And we can try to transition to a tougher formulation. Let's try and make the problem a little bit tougher. Can try to say, assuming the same list, I want to find a pairing of two numbers such that x plus y is equals to alpha. And I can say, for the sake of this example, that let alpha equals to 5. Say 5. Pick 5. So for this, if you want to exhaustively look into it, you can say I'll form all the possible combinations of my list of numbers ranging from 1 to 5, and I list them out: 1 and 2, 1 and 3, 1 and 4, 1 and 5. So this would be the first row. Then you go on to 2, so this is 2 and 1, 2 and 2, all the way to 2 and 5. And then the last row would be 5 and 1, all the way to 5 and 5. Now, because this is a very trivial problem, you can assign x and y to be, let's say, 4 and 1. This is a valid pairing. 3 and 2, this is also another valid pairing, uh, as well as 2 and 3 as well, also a valid pairing. Now, this is easy relatively because your n is equal to, in this case, excuse me, 5. And for you to actually um, guess the complexity here, I'll give you a moment here. Feel free to pause and give it some thought. The complexity here would be a fair 2 to the power of n, in which case n here would be equal to 5. So y to the power of n, because you have pairings of values, okay, not values themselves. So in this case, you'd consider this to be a slightly tougher problem to address, but not that very much of an aggressive leap on top of the previous. And the final problem would be primarily, of course, the NP hard problem, in which case the nodes would be an increase in the nodes would give you a very, very aggressive leap in your complexity. Let's try to see this in code on some graphs. Okay. Right here we have a problem in which we defined the set of problems that we discussed. We have the three problems. One is P, the other is NP, the last or the third is NP hard, along with their runtimes. And we do this over a set number of nodes, starting with 5 in increments of 5, all the way till 50. And we can see here that in green here, we have the O of n plot with input size on the x axis and the time, the runtime on the y axis, and both are logarithmic. So just bear that in mind. O of n problem scales awfully easily with increasing n. And the NP problem, we can see even on a logarithmic scale, on a logarithmic scale, it starts to scale slowly, not as aggressively as the NP hard problem, because we can see here that moving from 5 here to 10 in the number of nodes, we see several orders of magnitude increase in runtime, after which it times out after a hard limit set in code of 1 minute of runtime. We see here the O of n, 2 to the power of n, and O of n factorial uh, separately, and we see how aggressively they all, this one particularly scales, moving from 5 to 10, and the rest times out. This is just a graphical representation for you to see how things scale very aggressively when it comes to an NP hard problem. That it's a very tough problem to crack, one that I hope could be solvable in the future. Because if it is solvable, uh, a lot of problems would be a lot easier, and our lives will definitely be a lot easier because we wouldn't have the problems we have in many industries today. In general, I hope you all enjoyed the session. And I hope you enjoy the remaining sessions. Again, this is Fady Abouelghit, and I'm very happy you took the time to watch this session. I hope to see you soon in the upcoming sessions.